Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. So I hope that you are doing fine at your own home during this quarantine period, and welcome to the quarantine period again. And I hope that because this is not our first time, right? So I believe that you should familiarize and you should know how to adapt to it and how it works and everything. So just in case of anything, if let's say you have difficulties, just let me know. Okay, so we move over to, sorry, this is chapter 4, Thermodynamics of Solutions, Chemical Engineering Thermodynamics. Okay, first of all, we have to identify the definition of important uh, term in this chapter. The first one is phases. Phases is the part of the system that is chemically and physically homogeneous. Pardon me for the sound of the cat, right? Okay, and which is bounded by a distinct interface with other phases and physically separable from other phases. In the meantime, components are the smallest number of chemical entities necessary to describe the composition of every phase in the system. And what are solutions? Solutions is the homogeneous mixture of two or more chemical components in which their concentration may be freely varied within a certain limit. So it can be the subset of components, and component is a subset of the solution. And it is important that chemical engineers need to be able to estimate the degree to which a component will transfer into a different phase as a function of process condition. Because most importantly, it is to identify how species distribute among phases when more than one phase is present. Okay, pure species phase equilibrium. Okay, we take Gibbs energy that we have covered previously as criterion for chemical equilibrium, and the criteria for equilibrium can be formulated between two phases such as follows. The phases are generally labeled as alpha and beta that can represent the vapor, liquid, or solid phases. And firstly, the pure species equilibrium is addressed and determined that the derived property of Gibbs energy is a minimum at equilibrium. So only when two phases have equal values of Gibbs energy can they coexist. So this is the important point, because if the two phases have equal values of Gibbs energy, only then they can coexist. And secondly, the thermodynamics of mixture is addressed with partial molar property, which is K is a representative of the contribution of species I to the mixture. Okay, moving on. Since Gibbs GI sets the criteria for chemical equilibrium, it is often called as the chemical potential, or this symbol mu. In summary, the criteria of equilibrium between phases and can be written as T alpha equals to T beta, which is thermal equilibrium, and P alpha equals to P beta, which is mechanical equilibrium, and mu alpha and equals to mu beta, which is chemical equilibrium. As mentioned before, it needs to have two equal values of Gibbs energy of two phases. Only then they can coexist for the equilibrium. In analogy to the case for pure species, the criterion for chemical equilibrium between two phases for species I in a mixture is that the partial molar Gibbs energy G1 is equal in the two phases. Okay, so this is basically the concept of explaining about the equilibrium for the pure species phase equilibrium, which involve thermal equilibrium, mechanical equilibrium, and chemical equilibrium with different notations. And next one, Gibbs energy establishes the criteria for pure species by accounting for balance between the system's tendency to minimize E and its tendency to maximize S entropy. And at low temperature, energetic effects become more important, and at high temperature, entropy effects dominate. If two phases present alpha and beta, the total uh, Gibbs energy of pure species can be written as G equals to N alpha, G alpha equals to N beta and G beta, which is N is number of moles in phases alpha and B respectively. And G, of course, is the Gibbs energy. Right? Because I think this is really straightforward. You just have to determine the number of moles and then what are the Gibbs energy of each species. Equilibrium is a state at which the system no longer changes properties. Therefore, equilibrium occurs at minimum Gibbs energy. So, if G alpha lower than G beta, the species will transfer from phase beta to phase alpha, which means that the Gibbs energy increase of the system decrease, and only phase alpha will present at the equilibrium. Inversely, if G alpha is higher than G beta, the species will transfer from phase alpha to phase beta, whereby the Gibbs energy will increase of a system and only phase beta will present at the equilibrium. However, if the Gibbs energy alpha equals to Gibbs energy of beta, so the system reach equilibrium. And the criterion for chemical equilibrium is when the Gibbs energy is at the minimum, which is G alpha equals to G beta. So both exist, both phase can coexist. Okay, roles of E and S in phase equilibrium, and relationship between saturated pressure and temperature, which is defined by the Clapeyron equation, and how to relate P of a system in phase equilibrium varies with T. So if you still remember, by applying the thermodynamic web, okay, so you can refer to the thermodynamic web, how to relate it, and thus leads to analysis using Clapeyron equation. If assumed small liquid um, is negligible and ideal gas for vapor liquid equilibrium. So if you still remember the equation for Clapeyron equation, it can be defined and rearranged into Clapeyron-Clausius equation. Okay, so the Clapeyron equation is an expression that relates the P at which two phases coexist to the T of a system, and using the thermodynamics property relationships, which is a thermodynamic web. So we have this equation. It allows us to calculate the example how the saturated pressure changes with T to maintain phase equilibrium. So this is one of the important equation for you to really understand how it works, and especially because it's just the number of two phases, one alpha and beta, and you can get the saturated pressure temperature, the changes over T, so you can get the value. So this one also can be defined in this graph, but you have to rearrange it into um, the appropriate linearization. Okay, the thermodynamics of mixture. Uh, this section is to understand how property of species contribute to properties of the solution. For example, the binary mixture of species I and J, one should take into consideration the interaction between I and J and the interaction between I and interaction between I and J. The properties of a mixture depends on the nature and amount of each species. For example, if you mixed 50 ml of this chemical with 20 ml of water at 25 degrees C, ends up with 67 milliliter. Why? Because the solution has shrunk, because C2H5OH and H2O can pack together more tightly than can each species by itself. This is due to the nature of H bonding negative, which is more favorable than I I or JJ. Okay, so that's why it is defined by this. Even though it should be a 70, right? By mathematically speaking, it should be 50 plus 720. But if you mix together, in reality, it should be 67 because of this bonding of H. That is interesting to include in your test too. Yeah, I think I should play around with this understanding. So make sure you understand this one and this yeah, of course, this one. Yeah, this one, this slide, right? Okay, next one is partial molar quantities. What happens when we mix equal volumes of water and ethanol? This example show that we cannot simply add the thermodynamic properties of individual pure components and hope to come out with the total thermodynamic property of a system. Instead, we need the total volume of the solution comes out less than the sum of the pure liquid volumes. Why? Because the molecules interact and pack differently with each other than with like molecules. So this is the properties of solution, which is really interesting. And similarly, when an electrolyte such as magnesium sulfate is added to pure water, the volume actually decreases. This is because the polar water molecule condense around the changed electrolyte ions, an effect known as electrorestriction. Okay, so partial molar quantities is defined because most solutions do not mix ideally, but rather deviate from simple linear mixing as a result of atomic interaction of dissimilar ions of molecules within a paste. And partial molar quantities are defined by the true mixing relations of a particular thermodynamic variable, which can be calculated graphically by extrapolating the tangent at the mole fraction of interest back to the nth member composition. So this is the definition. If we define the partial molar K with respect to substance I, so we can get this equation whereby this one always in terms of N, never X, and this one always hold the intensive properties P and T constant, and this one the number of moles of all other species except I, which are held constant. Then we may write dk equals to k dn plus k to dn2, or the summation of this at constant temperature and pressure. If mole fraction, the composition of the mixture are kept constant, partial molar properties are also constant by following these equations. Okay, thermodynamic relation and partial molar quantities. So all the thermodynamic relations that we learned previously can be applied to partial molar function. For example, dg per dp equals to v. And similarly for the other thermodynamic relation also, to convert this to partial molar form, we take the partial derivative of both sides with respect to n. So we can get this. G equals to H minus Ts. So how this is how we want to get the relation between the thermodynamic properties and the partial molar quantities. Okay, next one is the chemical potential. The chemical potential. I think we continue after this. All right. Thank you.